everyone. My name is Sargam, and I'll be your teacher for geometry for math competitions. And you've probably seen my bio on the Alphademic website already, but I'm a freshman in New Jersey. I've been doing math competitions for around 2 years now, and as you guys probably know, my favorite subject is geometry, which is why I'm here today. And just for some information, we have a limit on how long we can meet for Zoom. So once we run out of time, you guys should join this link here. And today's class will probably be a review for most of you guys. So it's not really AMC 10 level just yet, but we'll be getting more into like harder stuff into later classes. And I'll give you guys access to the handout just in case we lag or anything. And just, if you have any questions, don't be afraid to ask. I don't bite. Also, I can't see the private chat on my screen, so if you have a question, you can say it out loud. Okay, so today we'll be covering the Pythagorean Theorem. So does anyone want to share what the Pythagorean Theorem is?
Do we just say it or?
Yeah, you can say it. You don't need to.
A squared plus b squared is equal to c squared.
Yeah, that's right.
It has to be a right triangle.
Yeah, so Alvin and I think Elisa also contributed. You guys are both right. In a right triangle with legs A and B, we would have a squared plus b squared equals to c squared. And yeah, Ethan, you're also right. And Pythagorean triple is just the ordered triple of numbers A, B, and C. So I assume you guys have some background in math competitions. You guys should know. Always have the 3, 4, 5, 5, 12, 13, 7, 24, 25, and 8, 15, 17 triple memorized. And we actually have a specific word for this where the 3 numbers are relatively prime. It's called a primitive Pythagorean triple. So here's just a checkpoint. You guys can try it out. You can chat me or raise your hand if you have the answer. Okay, so here's how you guys responded. First one is a right triangle, and the missing side length is 6, which is because 10 squared minus 8 squared is 36, and the square root of 36 is 6. Or you can just memorize Pythagorean triple. And Alvin,
Since it's 3, 4, 6, shouldn't the angle opposite of the 6 side be an obtuse angle?
Yeah, it should. That's a good observation, but the diagram is not to scale. I should have specified that. And I saw Alvin, you wrote in 5. That's right. That does make it a right triangle. And a lot of you guys wrote in the chat. For the most part, you guys are right. Okay, so now it's okay. So now we'll be looking at scaling up Pythagorean triples. Basically, that was what we did in the example before with the 6, 8, 10 triangle. It's when we multiply all the side lengths of a primitive triple by a certain positive integer. So for example, for the 3, 4, 5 triple, if you multiply all the side lengths by 2, you get 6, 6, 8, 10. And if you multiply by 3, you get 9, 12, and 15. And you can also do the same thing for 5, 12, 13. If you multiply all of them by 2, you get 10, 24, 26. And then this is also a concept that doesn't show up a lot in math competitions, but it's still quite good to know on the AMY. And it's just how you generate a Pythagorean triple using any random numbers. So the first number, the first leg would be m squared minus n squared. The second leg would be 2mn, and the third leg would be m squared plus n squared, where m and n are positive integers, but m is greater than n. And you can try to prove this in the homework, but proving it is mainly an exercise in number theory. And then another way you can generate Pythagorean triples is you can take any odd number, square it, and then represent it as the sum of two consecutive integers. So for example, 7 squared is equal to 49, and 49 is equal to 24 plus 25. And 24 plus 25, 24 and 25 are consecutive numbers. So 7, 24, and 25 would be a Pythagorean triple. So now we'll be looking at the Pythagorean theorem in 3D. So in 3D, we mainly use it when we have a rectangular prism or a cube or some sort of parallelepiped. And basically, if the prism has length L, width W, and height H, then the diagonal squared would be length squared plus width squared plus height squared. And if you want a specific example for a cube with side length S, the diagonal would be S root 3. And so if that doesn't really make sense how that formula came about, you can look at the specific cross sections for both the bottom and the top of the rectangular prism. So first thing, oops, sorry. 1 second. Let me try and annotate. Okay. So basically, first thing we're going to do for this image over here, we look at the bottom of the rectangular prism right here. And since it's a rectangular prism, we know that the bottom is obviously a rectangle, so this one over here is a right angle. So the blue dotted line is just going to be L squared plus W squared, the square root of that. But then we have the blue dotted line. So how are we going to get the red dotted line? So we have the height H over here, which we put over here. Not sure. Okay, so the key thing to notice is why does this form a right angle? Does anyone know? Might want to check the chat. Okay, so it looks like nobody knows. So the reason this is a right angle is because in a rectangular prism, the planes are perpendicular. So this one would just be a right angle since this vertical plane and this horizontal plane are perpendicular. So basically we just take this cross section and we put it here. So over here, the height H, this is the height H, it's over here. And then our second leg is going to be the blue dotted line, which we already calculated as the square root of L squared plus W squared. So now we can just apply the Pythagorean theorem again. We can get that this hypotenuse is the square root of L squared plus W squared plus H squared. Okay, so now we'll do a couple examples. You guys can try them out. And by the way, you don't have to raise your hand. Oops. You don't have to raise your hand. You can just say the answer aloud. Or chat me. So does anyone want to share what they got for the first diagram over here? Oh, something in the chat. Yep. So Alvin is right. So basically what we did, what we did, we basically did the same thing that we did in the last slide. So, you know, this one, S, obviously it's a rectangle, so this leg will also be 6. So then S, you know, S is going to be the square root 36 plus 400. 6 squared plus 20 squared. So now we have S squared plus the height, S squared plus 6 squared equals to D squared. So that means 36 plus 36 plus 400 is D squared. So D is the square root of 472, which you can simplify into 4 times 118, I believe, to root 118 for the first one. And then, does anyone have an answer for the second one? Yeah, so Alvin's right once again. Oh, sorry. So by the way, if I'm going too fast, you guys can let
Oh,
me
now it's no longer 40 minutes. Yay.
know. Yeah, so we don't need to access the link anymore. So does anyone want to explain how D is equal to square root of 3? Alvin, do you want to explain?
1 squared plus 1 squared plus 1 squared, then root it all.
Yeah, so that's right. Or you can just apply the formula we got in the last slide. So for a cube, you know, the diagonal is S root 3. So S over here is just 1, so it's just root 3. Okay, so let's move on now. So now we'll be looking at the law of cosines. So we'll be going over this in more detail in another class, but this formula is really important, so it's good to always have it in the back of your head. So in a triangle with angles, capital A, capital B, capital C, and the opposite side is just a lowercase letter, we have this set of formulas. So over here, you can actually derive the Pythagorean theorem just from the law of cosines, because the cosine of, say C is a right angle, then the cosine of C would be 0. And then this whole part would just cancel out. So a squared plus b squared would be equal to c squared. So does anyone know what cosine means in terms of a right triangle?
SOHCAHTOA. And so it's adjacent over hypotenuse.
Yeah, so this is our right triangle. A, B, and C. And this is our angle, C. So let's say this side is L, and this side is W, and this side is H. So the cosine of C would equal adjacent over the hypotenuse, W over H. But we'll be covering trigonometry in another class, so it's okay if you don't have this memorized. And just for context, these are just some common values of cosines. So for 30, it's root of 3 over 2. For 45, it's 1 over root of 2, or root of 2 over 2. And for 60, it's half. So now knowing this formula, you guys can try and derive these lengths. So does anyone want to try it out on the whiteboard? Or in chat if you're not comfortable. Okay, it looks like no one wants to try it out, so we can go through all three values. So the first triangle, and by the right triangle, special right triangle ratios, we have this order triple for side lengths. And we didn't really go over special right triangles yet. We'll go over that in another class. But this is just the triangle, this is just the side ratio for a 30, 60, 90 triangle. So then cos of 30 would just be adjacent over hypotenuse. So it'd just be the root of 3 over 2. Then similarly, we can find cosine of 60. It would just be 1 over 2. Then we can also do the same thing for a 45, 45, 90 triangle. So since it's a 45, 45, 90 triangle, it's isosceles. And we can use the Pythagorean theorem to find 1 squared plus 1 squared is 2. Square root of that is obviously square root of 2. So this cosine of 45 would just be 1 over root of 2, which we found here. Okay. This is a checkpoint. You guys can try this out and write your answer in the chat or aloud. By the way, in case you forgot, cosine of 60 is half. You can use that in your answer. Okay, so Alvin, it's okay. You forgot the law of cosines. It's fine. Does anyone? Oh, so Alvin, do you want to share the law of cosines in case anyone else forgot it? Close, but still a little bit off. Does anyone remember the law of cosines? Want to share it in the chat? Jenny, do you remember the law of cosines? Okay, so I think we went over that slide too fast then, so let's go back. So you guys can take notes. So in a triangle, let's just do it on our own. This is a right triangle. No, sorry, not a right triangle, it's just a random triangle. A, B, C. Let's call these side lanes A, B, and C. So the law of cosine says that C squared plus B squared minus 2BC cosine of A is equal to A squared. And then okay, so just fast with cosine, we can go over that. So let's go over what a cosine is. So say we have a right triangle. Oh, and by the way, I might say cosine, I might say cos sometimes, just know cos is just an abbreviation of cosine. So back to that. Say we have a right triangle A, B, C. So in a right, let's call these side lanes, length and width. So cosine, so basically the cosine of the angle C is equal to W over H. So let's look at an example. So say this one is C and W equals to 2 and L equals to 1. Then H is equal to 5, root of 5 by the Pythagorean theorem. So then the cosine of C would be 2 over the square root of 5. So does that make sense?
Can you do that again?
Okay, sure, I'll do it again. Okay. So let's take our right triangle. And B is a 90-degree angle. So let's name our side length. So say BC is equal to L, AB is equal to W. Let me write that down. AB is equal to W, and BC equals to L. So by the Pythagorean theorem, AC would be the square root of L squared plus W squared. It's also known as the hypotenuse. We can abbreviate it as H. So this angle is C, right? C. So the cosine of C is equal to adjacent over hypotenuse. So adjacent means it's just the side that is right next to the angle. That's not the hypotenuse. So over here it'd be length over hypotenuse, H. That's what a cosine is. So does that make sense?
Yep.
Okay, great. And I'll just go over an example. So let's say length equals to 2 and width equals to 2. So then the hypotenuse would be 2 squared plus 2 squared, right? 4 plus 4, which is the square root of 8, equals to 2 root 2. So then the cosine of C would be length over hypotenuse, which is 2 over 2 root 2, which is 1 over root 2, as it says right here. And in the future, we'll be going over how to calculate C exactly. Most of the times we can't do it manually, but when we have special angles, we can actually do it by hand, but we'll be covering that later. But if you want to try it out now, you can just do, if you have a calculator in hand, you should see a button that says cosine to the power minus 1. And then you can put in your value, 1 over root 2. And if you plug that into a calculator, you'll get 45 degrees. But that's just extra. You don't have to worry about that right now. So let's go to our example. And I'll put the cosine value of 60 up. And does anyone remember the law of cosines? Anyone want to share it? Alvin, do you remember? Okay. Yeah, so Ian's right. Oh, sorry. Ethan's also right. And in this context, it would just be C squared. A squared plus B squared minus 2AB. Let's call this angle C. Cosine C equals to C squared. C equals to 60. So once you're done, you can just say it out loud, chat me with the answer. So Ethan, do you have an answer? Okay, it's fine. Take your time. Ian, do you have an answer? Okay, Raymond, that's right. Raymond, do you want to share how you did it? Yeah, Doreen, you're also right. Anyone with the right answer want to share?
So, how do you get the answer?
I just put the sides into the formula.
Yeah, that's basically just it. It was just plugging stuff in. So over here, you know, A equals to 40, B equals to 30. And we're given, since C equals to 60, this whole thing is equal to half. So it's just 30 squared plus 40 squared minus 2 times 30 times 40. Cosine of 60, which is half, equals to C squared. And once you calculate that, you'll get C is the root of 1300. Okay, so did that make sense? Anyone have any questions on what we did so far? Okay, seems like there's no questions. But for now, this course is focused on math competitions, and the problems we did so far, they were just really straightforward. But on math competitions, usually the right triangles aren't so obvious. You have to find out stuff yourself because it's more word problems. So here are just some strategies to look for in math competition problems. So the first thing to look for is similar triangles. So does anyone know what similar triangles means?
Triangles that are alike, except some could be like bigger, like there can be a 9 and 3 and a 4 triangle, and there can also be like multiplied all of the numbers of the triangle by 2, which it would be basically the same triangle but a bit bigger.
Okay, you're right. But Samuel, do you notice this just extra? Do you notice anything wrong with this triangle?
Well, yeah, because this can't actually be a triangle because 4 plus 3 does not equal 9. But
Yeah.
it's just like an example.
Yeah, that's right. But we'll just pretend that this is a triangle. Or we can just make it a triangle. Let's say this is 7. 7. So what Samuel said is true. Basically, similar triangles just have the same ratios. Say we multiply everything by 2. These triangles would be similar since all their angles are equal and all their sides are in a common ratio. And in the future, we'll go over how to find, Ian, you're also right. Same angles, different scale size, basically the definition. And in the future, we'll actually go over different techniques for triangle similarity. Oh, Doreen, I see you solved this problem over here. That's great. X is, 20 root 5. Yeah, just the Pythagorean theorem. And okay, let's get back to what we're doing. So always try to use the Pythagorean theorem when you see a triangle. So you should always drop altitudes, drawing your own right triangles and other stuff involving right angles. So what do I mean when I say drop the altitude? So drop the altitude means, say we have a triangle here. A, B, C. So let's say someone tells me drop the altitude from A to BC. So I just drop the altitude from A to BC. This is called dropping the altitude. It's basically just drawing the altitude to that side. And this is a useful technique because often you can use the Pythagorean theorem, find missing side lengths, find area problems, etc. And then tangency problems we haven't really gone over yet, so we'll skip that for now. And also for isosceles triangles, you should always draw an altitude because with that, you can often find the area, find the perimeter, the height, something important. Okay, so now, does anyone have any questions? Because we'll be doing some hard problems now. Or I'll just go back real quick. If anyone needs anything, they can. If anyone wants me to stop, you can just tell me. Yeah, to answer Doreen's question, I will post them in Google Classroom so you can review them in the future. So does anyone have any questions about this? Because it's a pretty interesting thing. I think it's pretty hard. Generating triples. No? Okay. Pythagorean theorem in 3D. Does anyone want me to go over this? These problems. Law of cosines we went over, but if anyone wants me to review one more time, we can do that. Checkpoint 2, we just did. Okay. So now we'll start some sample problems. So in trapezoid ABCD, the sides AB and CD are equal. The perimeter of ABCD is, and I'll give you guys some time to solve this. Once you have the answer, you can say it out loud, chat me, as always. Also, if you need a hint on any problem, you just can't seem to make progress, you can also let me know. Does anyone have an answer? Yeah, Doreen's right. Doreen, do you want to explain how you did it? if you're comfortable. It's fine if you're not. Okay, so I'll just follow along with your explanation. Joseph is also right. Yeah. Okay. So this is a trapezoid. And since this is also in a trapezoid, both side BC and AD are parallel. So that means this height will also be 3. And as Doreen was saying, 16 minus 8 divided by 2 is 4. So both this one, this side over here, and this side over here will be 4, since it's an isosceles trapezoid. So that means, okay, we can actually prove this. So AB is equal to CD. Let's just backtrack. So if AB is equal to CD, then that means by the Pythagorean theorem, AX and YD must be equal. So both AX and YD must be 4. Then we can use the Pythagorean theorem again. AB is 5 and CD is 5. So then we can just add it up. 10 plus 8 plus 16 is 34. So that's our answer. And here's the official solution. Did everyone get that, or does anyone want me to go over it one more time? Okay, seems like everyone got that. But if you didn't get it, you realize later, please let me know in chat. I'll redo it. Okay, so this is our second problem. Angle ABC of triangle ABC is a right angle. Sorry. The sides of ABC are the diameters of semicircles as shown. And the area of the semicircle on line AB is equal to 8 pi. And the arc on the semicircle on AC has length 8.5 pi. So what is this radius of the semicircle on BC? So does anyone know what formulas we need to use for this problem about circles? So does anyone know what the area formula for a circle is? Yeah, pi r squared. Yeah, pi r squared. So the area, oh, sorry. Oh man, okay. Yes, I knew you're going in the right direction. So area, oh man, sorry. So the area of a circle is pi r squared, where r is the radius. And does anyone know what circumference is? The formula for circumference?
Two pi r.
Yeah, that's right. Nice job, Samuel and Alicia. Yeah, that's also right. Circumference is equal to 2 pi r, or d pi, where, once again, r is the radius. And 2r is equal to the diameter, so that's why both of these are the same thing. So what are we giving? The area of semicircle on AB is equal to 8 pi. And the arc has length 8.5 pi. Is the radius 8 for BC? I don't think so, but you're very close to the actual answer. Ian. So Ian, do you want to share how you did it? How did you get 8? Okay, it's fine then. So over here it says the arc on the semicircle on AC has length 8.5 pi. So does anyone know what the radius of this circle would be then? 8.5. Yeah, and that's right. Because we can, since this is the arc of a semicircle, so we know that the circumference of the full circle is 2 pi r, but a semicircle is half of a circle. So we need to divide by 2. So this means that the radius equals to 8.5. So then if the radius is 8.5, does anyone know what AC would be then? $17, yes. Nice job, Joseph. Raymond? So AC would be 17. So now let's do the same thing for this semicircle. Yeah, Doreen, you're right. Nice job. Oh, Doreen, actually, I think you made a little mistake. You find the diameter, not the radius. So the radius would just be 15 over 2. But anyways, back to the problem. So the area of this semicircle is 8 pi. So yeah, and you're also right with the final answer. So we know that the area of a whole circle is pi r squared. So what would be the area of a semicircle, which is half a circle? pi r squared over 2 is the area for a semicircle. So then pi r squared over 2 equals to 8 pi. So pi r squared equals to 16 pi. So r is equal to 4. So the radius is equal to 4. So does anyone know what AB would be then? So AB, okay. Yeah, Samuel, you're right. AB would be 8 since it's the diameter. So now, what are we given? We're given that ABC is a right angle. So let's use the Pythagorean theorem on triangle ABC. So BC would be BC squared plus 8 squared equals to 17 squared. So we can calculate BC squared equals to 225. Or BC is 15. But our final answer isn't 15. We have to find the radius, not the diameter. So the radius of the semicircle is 15. Sorry, the diameter is 15. So we know that the diameter divided by 2 equals radius. So 15 over 2 is our radius. And that's our final answer. Or 7.5 if you prefer decimals. So did that make sense? Does anyone have any questions? Okay. So we can try one last example. We have a couple minutes left. This is the official solution, which is exactly what we did. So this is a very hard problem, and I'll give you guys some time to try it out. I'll draw a diagram just to help you guys out a bit. So does anyone know what concept we need to use in this problem? We didn't really go over it, that much in class, but we did briefly mention it. Starts with an S. Yeah, so Ian's right. So Ian, do you know how we would use similar triangles in here? Or what triangles are similar? WBZ is similar to ABC. That's right. And do you notice any other similar triangles? Notice that this is a square. So this is a right angle as well. This is also a right angle. Yeah, so Ian's right. And how can we use this information to solve the problem? So let me just bring up the official solution since this is a lot to write. Okay. Okay, so this is just the same drawing, it's just horizontal. So BC is 4, AB is 3, and AC is 5. This is 5. And we need to find out S. So, as I said, WBZ is similar to ZYC, is similar to ABC. And you can also note this triangle is similar. We didn't really cover this, but it's because the angle is A here. It's going to be 90 minus A, which is the same angles as the big triangle ABC. So since it's similar, we can say that BZ, this is a square, BZ is to S, is equal to 4 is to 5. Since BZ is this leg, the BZ leg corresponds to the leg of 4 in the big triangle. Angle C is equal to angle W. Okay, so I'll go over that. Okay, so let's go over it. So this is a right angle. We're given that, right? And BC is 4, AB is 3, AC is 5. So let's say this angle is A. And a square, we know that a square has all right angles, so all of these would be 90. So since this is 90, this is also 90. Since we know a straight line is 180 degrees, 90 plus 90 is 180. So if this is 90, we know this one is 90 minus A. And then this is a right triangle, right? ABC. So if one angle is A, then this angle over here is 90 minus A. Since ABC is a big right triangle, we need angle A and angle C to sum to 90. So this is also a right angle. And we need 90 minus A plus angle W to equal 90. So W has to equal A. Does that make sense? Yeah. Nice job. So BZ, so now we have our similar triangles, right? So in this example, we'll just be using WBZ, ZYC, and ABC. Okay, so let's draw them in. WBZ. Oh, and we can also prove that WBZ is similar because this is 90. And then this would be A. since 90 plus 90 minus a is equal to 180 minus a, and this is a straight line, right? So this angle has to be a, right triangle, this one has to be 90 minus a. So that's how you just prove it. ZYC, ZYC, and of course, A, B, C. Okay. So this is BC, and we know WZ is equal to S, the side length of the square. And we also know that YC is the side length of the square, and those are the only sides of the squares in the diagram. So since these triangles are similar, WBZ and ZYC, we have BZ is to S as BC is to S. Let me just draw this in. BC is 4, AB is 3. Now all three of these triangles are similar. And as we said before, the similar triangles, their side ratios are always the same. So over here, BZ is to S would be equal to 4 is to 5. And S is to ZC would be equal to 3 is to 5. So from that, we can find that BZ equals to 4/5 S. And ZC is equal to 5/3 S. So now we can label our diagram. BZ would be 4/5 S. And ZC would be 5/3 S. And we know that this leg is equal to 4. So that just means 4/5 S plus 5/3 S is equal to 4. And we can solve for S. S is equal to 60/37. Did that make sense? It was a little complicated, so we'll be going over it in another class. Okay, so I think that's all the time we have for today, if anyone doesn't have any questions. So I hope you guys learned a lot about the Pythagorean Theorem, triples, the law of cosines, and I'll be assigning a set 10 problems for homework that are due by next Sunday. And if you have any questions, you can email me at sargammondal@alphademic.org, or you can post a private comment on the assignment. So that's it for today. I hope you guys enjoyed.